Hello, and welcome to part 8 of this series of videos that introduce the mathematics of signals. For a playlist with all the episodes, please click the link at the top of the screen. In this episode, we're going to introduce the complex Fourier transform. So here's a quick outline. We're going to answer questions such as, how can we change Fourier series, which we saw in parts 4 and then complex version in part 7, to represent non-periodic signals. We're then going to see what effect this has on the spectra it computes. And then we're going to introduce the concept of spectral density that arises from this. So we're going to look from going from a Fourier series to a Fourier transform. So far, we've been assuming that the signals we're representing are exactly periodic with some time period, big T. So if you looked at the signal versus time, you just keep on seeing lots and lots of copies of the same thing happening over and over again. That's what the type of signal we're looking at. But that is really rather restrictive. That's not how signals behave in the real world when you measure them. It's unrealistic too. So how can we drop this assumption but keep all the mathematical machinery of Fourier series, which is shown to be so useful, working correctly? Well, the trick in short is to take the time limit as t goes to infinity. If you just make the repeat period infinitely long, then the signal never repeats. So in a way, that's it. But there's various implications that will come out of this, so we need to look and see what effect this has. So first of all, let's think what happens. The first step is to lengthen the repeat period. So take the limit as period t goes to infinity. So here's a signal. I've just drawn this time period t that we're assuming is going to be the repetition length on here. And if you drew its spectra, you would see, because it's a Fourier series, you'd see a series of these discrete frequencies where we have some amplitude xn. So those are the fn's. I've just sort of plotted little vertical lines out here. And the spacing of those, delta f, is 1 over t. So what we're going to see as t gets longer is that delta f, which is 1 over t, gets smaller. So as we assume that our signals include more and more time before repeating, these harmonic frequencies, these fn, are going to get closer and closer together. So that is the first and important thing that's going to happen. The lines are going to get very, very close together. And if you go to infinity, they're going to get so close that they completely touch. So that's the first thing. The second thing is that we're going to change the normalization of all of this. And I'll just try and explain this and how it's all going to work. So we start with our signal xt in the time domain. And if we're doing Fourier series, we do this first integral here, which I tend to call the analysis integral, the forward transform. It works out what component of different Fourier harmonic frequencies are in there, so we get these amplitudes xn out of there. And it's this integral of the signal times e to the I2 pi fn, the frequency we're looking for, t with respect to time. And usually I've been writing this 0 to t, but it's going to suit me here to write minus t over 2 to plus t over 2. And that's okay because the signal's periodic, it gives the same thing. And then to get back to x again, we go through this other statement, which I tend to call the synthesis, the reverse transform. And that synthesizes the signal xt back from this series of complex amplitudes xn. And just to point out first of all, xn and xt and xn have the same units. They're both amplitudes, both have the units. So if xt has pascals for pressure, then so will xn, or if it has volts for voltage, so will xn. It'll be the same. Now, from the reverse synthesis integral, that's probably quite obvious because xn has units, e to the I2 pi fnt doesn't. Just add all those terms up, they all have units, and xt has the same units. So that just all kind of follows through. The term on the left's a bit more complicated. We have an integral here. So it's the area under the curve, and the vertical axis has the units of xt, because that's what's in there. E to the I2 pi fnt again doesn't have units, but then we integrate with respect to time, and time does have units, it has units of seconds. So the area under the curve, what that integral is producing is units times seconds. And actually what we then have is a 1 over t, which gives you a 1 over second, so that cancels it back out and we're back to just units for xn. But yeah, you'll see in a little minute why I'm emphasising this. So the first step, the first thing we're going to do is we're going to change our term at the bottom, the actual way we define these amplitudes that we're transforming to. And rather than working with xn, which is an amplitude, we're going to work with a term I'm going to call xn, d, and the meaning of the d will come through in a minute, and that's going to be t times xn, so it's going to be multiplied by t. And if we wanted to calculate that from the analysis integral on the left hand side, we'd obviously multiply the whole thing by t, and that will get rid of the 1 over t. So we're going to see this all kind of change. So if we're going to move to xn, d at the bottom, the 1 over t is going to be removed from the analysis integral, but then we've still got to go around this cycle. We've still got to kind of make everything work both ways. So we just go around the cycle and everything. You start from a signal, you go to the transform, you come back again, you get the same thing. So if it's not going there, it's going to have to go on the other side. So it's going to move. So we'll see that now it's vanished from the left hand side and now it's appeared in the synthesis integral instead. So we've got this new term xn, d at the bottom. And all that's changed is that 1 over t's moved, but we've now got different units. So because we've got t times, then we know that these are going to be times seconds. So it's got the same units as x of t, but multiplied by seconds. And this is consistent with the integral again. We had the signal on the vertical axis, whatever its units were, times seconds along the time axis, horizontal axis. The integral is the area under the graph, which is giving us xnd, so that has units, the same units as x of t, the signal times seconds. Going back through the synthesis integral, well, x and d has the units of x times seconds, but then we've got a 1 over seconds arriving from the 1 over t, so it all sorts itself out. Okay, so far, nothing much very exciting going on. So what's going to happen next? Well, this 1 over t on the left hand side now is something interesting in this synthesis integral, because it actually has a bit of a meaning. If we plot this on the graph again and we plot this spectra, you can see all these lines representing these different frequencies in the Fourier series and their different amplitudes xn, d, but they're all spaced by 1 over t. So actually what 1 over t times xn is, which is what you get if you moved 1 over t inside the summation, is actually a little rectangle, and these all sort of just join up, and we've got a little collection of bars which gives us an area under the curve. And as you will have seen a couple of times in this series of lectures, when you kind of do that sort of thing and you turn a collection of discrete values into little rectangles, what you're doing is heading in the direction of saying, well, actually what we're doing is working out the area under this, and we're actually going to turn this into an integral in a minute. So you can probably see what's coming. The synthesis term is going to turn into an integral, and it's that move of that 1 over t that's has allowed that. And this also makes us think, well, hang on, maybe there's not just amplitudes just at those Fourier frequencies, maybe there's some amplitudes at some other frequencies in between instead. So rather than writing xnd, I'm going to just start writing xd of f, and acknowledge that this xd of f, this kind of continuous distribution of what might be happening at any frequency, has just been evaluated by the Fourier series at a fixed set of frequencies, fn. So that xnd I had as this kind of term as an intermediate term on the last slide. I'm going to it's just that this continuous distribution x of d evaluated at fn, at the Fourier harmonic frequencies. Okie dokie. So that kind of bodes the question, can we evaluate xd at some other frequencies too? And the answer is yes, so long as you take the limit as t goes to infinity, which is what we did before. So you can only evaluate with the Fourier series at a harmonic frequency. But if you let t go into infinity, you get an infinite number of harmonic frequencies that are also infinitely close. So you can evaluate at any frequency. So rather than being restricted to xnd on the left hand side in the analysis integral, we'll just switch that around and we'll replace fn with f, and we'll just say that what we're going to do is evaluate xd at any frequency, and now my t over 2 and my plus t over 2 have gone to minus and plus infinity because t had gone to infinity to let me do this. And I'll just carry this sort of thing around the circle. So at the bottom here, I don't need to say fn anymore. I can just say x of any frequency f I like. And then in my synthesis integral, well, we already said this was going to turn into an integral. I just said it already. Yeah, that summation with all the little bars becomes an approximation to an integral, and when the bars get infinitely close, 0 distance apart, then it actually is an integral. So there's no equality or sort of approximation here. It is actually equal. It is an integral. And that is our Fourier transform cycle. We got there via a couple of steps, but really all we did was we changed the repeat period to take the limit as t went to infinity, and we changed the normalization. So there's a few little sleights of hand, turning a summation into an integral, and you kind of have to get things in the right place first, but essentially it's just follows from taking the limit as t goes to infinity and changing the normalization. Let's just look at those units again. So xd of f has again been worked out by an integral, albeit an infinite one, where the vertical axis is the units of the signal. We're integrating with respect to time in seconds, so xd of f has the units of xt times seconds. So there we go, there's that again. And the same as writing times seconds is we can write divided by hertz. So rather than saying it has the units of x times seconds, we can say it has the units of x per hertz. And that will turn out to be the way that we talk about it. That we will say that it is a density, a quantity per hertz. It is, of course, a function of frequency, so that's kind of the logical thing to say. And this works with the synthesis integral going back again, because now what we want is that this integral, the area into this graph, has the units matching x. So if we're going to integrate that with respect to hertz over frequency and expect that we get the right units, then the quantity xd is going to be in has to be units per hertz. So this is one of the fundamental things, is that you find the units of xd is the same units of the signal per hertz. It's an amplitude density is what we call it, a density in frequency. So that is it. Whether or not you're comfortable with that is a different question, but those are the two equations. That is the Fourier transform. It's just a different version of the Fourier series. So just to surmise, the reverse transform is now also an integral. They now both run from minus infinity to plus infinity. Over time for the forward transform, over frequency for the reverse transform. And this frequency domain quantity, xd, d for density, of f frequency is now a continuous distribution in frequency, and it's an amplitude density, which means it has the units of the signal xt divided by hertz. Finally, I'll just mention the difference between lines, bins and spectra. These are some words you'll see being tossed about when we talk about Fourier transforms and Fourier series and FFTs, which I'm going to talk about in the next talk. So a Fourier series is what you might call a line spectra. I've drawn it this way a couple of times here. So we only get some discrete frequencies, some discrete points on the horizontal axis where you get anything at all, and at those you just get some amplitude. So this is can be drawn as like a stem plot or a line plot like this. On the other hand, over on the right hand side we have a Fourier transform, and we've seen that gives you a continuous spectra xd of f. And this is a continuous function in f, so it's a continuous spectrum. And the concept of bins, people tend to say FFT bins, where FFTs are the algorithm for evaluating these, as we'll see later. Is this kind of halfway house where we've got this these little kind of rectangles, and what you're saying there is that the name bins acknowledges that the FFT lines really have some finite bandwidth, and what exactly their bandwidth is it's not quite as simple as a rectangle, but they have some finite bandwidth, and they also collect energy from xd that falls in between the lines from a sort of surrounding area. So they're not just collecting energy just at that. When you take an FFT, you're not getting energy just bang on the frequency it says it is, you're getting energy from just around about as well. And this term bins comes from histograms, which, for turning continuous data into discrete data like this. So that's where the name comes from. It's a histogram over XD. Okay, so that is all for this topic. Some fairly sort of, sophisticated little maths manipulations there, or depends how comfortable you are with integrals, but it's just stepping through the maths really is all we've had to do. So Fourier series was appropriate for periodic signals. It produces a line spectrum, amplitude xn at a set of discrete frequencies fn. Xn has the same units as xt. And the forward transform analysis was an integral from 0 to t to big T, or minus big T over 2 to plus big T over 2 as we saw. Whereas the reverse transform, which is called synthesis, was a summation with respect to n, which is an integer, from minus infinity to plus infinity if you do it all the way. Often we'll truncate this, of course, when we're evaluating things really. The Fourier transform generalises this concept to non-periodic signals. It produces a continuous spectra, xd of f. And xd is an amplitude density, that's what the subscript d is intended to mean here. It has the units of x divided by hertz, so it's amplitude per hertz. And both transforms are now integrals, and both run from minus infinity to plus infinity over time for the forward transform and over frequency for the reverse transform. So that is it on Fourier transforms. Quite a sort of abstract concept perhaps for some people who are more rooted in engineering and acoustics and audio. But next time we're going to take it a bit more real, and we'll talk about how to compute a Fourier series on a sampled signal, as you'll often have in digital audio, and then we'll bring it all together and say how we're going to estimate one of these Fourier transforms using everything we've learnt so far.